The one and only Pawel.
Thank you very much, Victor. The one and only Victor. So thanks a lot for inviting me here. I actually have, at least I've been discussing with Jules in the last few months about doing something together. And I originally wanted to present that here, but I didn't quite manage to have enough time to prepare this. So this talk is only going to be tangentially related to open games. And I've tried to at least make that tangent fairly clear in the first few slides. So the first slide is kind of an overall mission statement, which also keeps evolving, of the kinds of stuff that I'm interested in. And I would say, I would make the claim that when we start to study the mathematics of open things, various kinds of nets, circuits, computational models of computation, even games, they involve the study of various kinds of relations, right? So when you look at the mathematics of what you get, when you sort of divide behaviors and try to assign behaviors to these open artifacts, they're not going to be functional, they're going to be relational in various ways. Okay, so open systems lead to us caring about relations. So now, since we want to understand relations, we're going to want to study algebras of logics, or algebras of logics, which give us operations for constructing or maybe deconstructing examples. So we want to be able to study complex compound systems compositionally by decomposing them into the primitive components. We want to then, understand, let's say, maybe the kind of relation that we get as a behavior of the individual bits, and then perhaps perform some kind of computation like we saw in Brendan's talk, more efficiently, knowing that you have a compositional specification of a system. And historically, we have a number of sort of famous languages available. For example, first-order logic is a language that allows us to talk about relations and their properties. But there are some more specific things that came later. So probably the most famous is relational algebra. But on the category theory side, we also had allegories. But we're going to go in the path of using monodal categories. Okay, so somehow there's a lot of this is somehow what I've been doing in the last 5 years. But once we have these operations in which we can construct our examples, which in my work tend to be monodal categories, we want to then understand how can we reason about these systems. And so these will involve, drawing our systems as string diagrams using diagrammatic reasoning, but also typically involve additional equations that are domain-specific for any particular operation, right? So it's about finding equational presentations of the kinds of things that you're interested in. And some examples that probably people know about if you take Rel Plus. So this is the category of relations where monodal product is the coproduct. It has a kind of a very simple equational presentation as the theory of special bimonoids. Then there's graphical linear algebra, which is the category of linear relations, and it's the theory of interacting Hopf algebras. Then, of course, if you know about Brendan's work, Brendan was interested in many of his examples in correlations, and just sort of the vanilla correlations, just the most simple example is the theory of extra special Frobenius. And we have exciting stuff in the pipeline. So in particular, I think Robin has made some really incredible discoveries in the last few months. So that's going to come soon. But in this talk, I want to talk about Cartesian bycategories, right? So, and I'll sort of motivate what is the interesting thing about Cartesian bycategories and how they are related to this overall goal of trying to understand relations, algebraically, equationally, etc. Okay, so the talk in one slide is that free Cartesian bycategories are extremely cool things. Okay, so why is this? By the way, if you don't know what Cartesian bycategories are, I'll explain it all in detail. These are Cartesian bycategories are things that sound extremely difficult, but are in fact extremely simple. So it's one of these things that have been named in a bad way, because when you hear Cartesian bycategory, you think, oh my God, this sounds really terribly difficult. But then you read the definition. Actually, the original definition is also not written particularly well. But when you translate the definition into string diagrams, then suddenly you go, oh wow, this is amazing. This is so easy and beautiful. Okay, so Cartesian bycategories are basically, we take this monodal approach to talking about relations, and in particular we're going to be interested in real times. So the category of relations where the monodal product, or the monodal category of relations where monodal product is Cartesian products. And we'll see that, so Cartesian bycategories give us just the basic monodal structure plus some additional constants as part of our language. And you'll see that what this kind of gives us is a language for databases and queries on databases. And it turns out, moreover, that this is something that database theorists have known for a long time, except that in database theory, this is called a calculus of conjunctive queries. Okay, so this expressivity of Cartesian bycategories as a logic is the same as the expressivity of this famous calculus of conjunctive queries. But it has the advantage of not being a fragment of first-order logic and being stated in a categorical way. So, for example, it gives us this idea of a functorial semantics. So, what is a database or a model of these queries? Well, it's simply going to be a structure-preserving functor to real times. And perhaps the most interesting and important aspect is that Cartesian bycategories come with an equational theory, right? And this equational theory is very canonical, right? Because it's a sound and complete characterization of this notion of query inclusion. Okay, and I'll explain what I mean by sound and complete, but it's kind of complete in this classical logical sense of complete, right? So if something is true in all models, then it's also derivable in the logic. Okay, so I'll start with telling you what conjunctive queries are classically. So this is the calculus of conjunctive queries. So you see it's a subset of first-order logic where we have relational symbols, we have conjunctions, we have equality of variables, and we have existential quantification. So the typical thing in first-order logic is, okay, if you're going to start defining models of these things, right, so I take a formula with some free variables, and then I'll take the model. To give a model, I need to pick a set, pick relations of the right arities in the standard way, right, and the meaning of a formula with free variables will be just all the assignments, all the possible assignments to free variables that make this work. So it's, another way of saying this is all the results that satisfy this query. So you think of the formula as a query, and you think of its semantics as all the results of the query, right? Where the results are specified as the free variables of the formula. These are the things that we're interested And when you think of the expressive power of this, it's, well, as I said, it's well known in database theory and some kind of a core calculus that expresses things like select, project, join in relational algebra, select from where in SQL as the core of data log, and you know, it's one of these things that appears in a whole bunch of important things. And the reason why it's interesting is because there are some classical results about computability of various semantic properties of this logic. Okay, and one of the most natural canonical properties is this notion of query inclusion. Okay, so once we give, you know, I'll give you a formula in this logic, I'll give you a model. So query inclusion says it's basically a semantic pre-order on formulas, right? So I say that a formula phi is less than or equal to formula psi if in all possible models the meaning of phi is included in the meaning of psi, right? So the results I get for query phi are a subset of the results I'll get for query psi. Okay, and this is one of the most famous results in sort of classical relational database theory, that query inclusion is decidable in NP complete. And actually the proof is super interesting, right? And the proof essentially translates formulas into hypergraphs with interfaces. And I'll give you a little example on the next slide. And then this notion of query inclusion reduces to a combinatorial problem about these hypergraphs, right? So the idea is that we're looking for the existence of a hypergraph morphism that preserves the interface. So we can find this hypergraph morphism, and then it follows that query inclusion holds. Okay, so here's just a little example. So we start off with two formulas, sort of two queries in the calculus of conjunctive queries. And more or less, the translations in Chandra and Mellon work like this, right? So the relation symbol here is a binary relation symbol. So this is going to translate to a hyperedge with two legs. Now, both these formulas have the same interface. The interface is just the free variables. So they both have free variables x0 and x1. And so this is kind of represented by this set of nodes, which represents the free variables. Then the other nodes in each hypergraph represent variables that are in the formula, that appear in the formula. But the ones that are not in the interface have been existentially quantified over. Okay.
Z0 and Z1 are those all in the right?
So Z0 in this formula would correspond to this node here, because it's not seen from the interface, right? So it's a variable, but it's not available. And here we'd have Z0 and Z1. Okay, and you can see that there's a homomorphism now, a graph homomorphism from this graph to this graph, which just kind of collapses everything and preserves the interface. So, you know, the obvious commutative diagram commutes. And this tells us, according to Chandra and Mellon, that there's a query inclusion holding in this direction, right? So everything so in any model, if I take this set of results that satisfy this query, it's going to be a subset of the ones that satisfy this query. Okay, so it's an interesting little connection between logic on the one hand and these combinatorial structures on the other, which is another thing that we'll kind of hopefully clarify in this talk. Okay, so this is kind of the triangle. And we're going to connect logic, algebra, and combinatorics. So first of all, we're going to redefine the logic and talk about something slightly nicer than first-order logic, even though it has the same expressive power. And we're going to give this, the idea is we're going to give a characterization of query inclusion, which will turn out to be precisely the equations of Cartesian bycategories, as I advertised previously. Okay, and the way this proof works is it really takes advantage of this deep relationship between Cartesian bycategories and certain code spans of hypergraphs. Okay, and this is, I will explain how that works, and together this kind of gives us this nice little connection between these three things. Okay, so first of all, let's start by throwing away the logic, and let's talk about monodal categories. So I'm going to define something called graphical conductive queries. No, conjunctive, this is a typo. Okay, so it should be graphical conjunctive queries. So essentially, I'm just going to build up, I'm going to introduce a little language of string diagrams, okay, where I have a comonoid, a monoid, and relation symbols. Okay, I'm going to draw these things. So these are my basic building blocks of string diagrams. And now what is a model? Okay, so for now I want to just think of this as a logic, right? So this is so for that reason I had to throw in some additional stuff like, you know, the identity on zero and the identity wire and the twist.
Be a plus and semicolon the way around that you want them to be there?
No, that is a typo, I'm sorry. Yes, so plus should be stacking and composing should be. Indeed, well spotted. Okay, so what is a model of this thing? So I need to choose a set X, and the diagram I'll construct from this signature with M left dangling wires and then right dangling wires will translate to a relation, so a subset of x to the m times x to the n, so a relation from x to the m to x to the n. And this mapping will only depend on whether the relation symbols are sent. Why is that? Because these basic components always have a fixed meaning, right? So not surprisingly, the meaning of the co-multiplication is simply the diagonal relation. The multiplication is just as suggested by the notation, is just going to be the opposite relation. And these are the obvious co-unit and unit for the structure, which are just the full relation, right? So this is a relation from x to x to the 0, and this is the unique element of x to the 0, the bullets. So that's how I interpret the basic components. Obviously, these things shouldn't really shock anybody. So I just need to tell you about. Okay, so the interpretation of a relation symbol is just this, you know, this part of the model that I have to give you. I have to tell you what the relation symbols mean, and the interpretation of the two operations is, this should be the Cartesian product. Again, I'm sorry, this is a typo. So I'll just take the Cartesian product of relations for the monodal product, and I compose the relations in the usual way for the composition. Okay, so the interesting thing is that graphical conjunctive queries have the same expressive power to the ordinary classical calculus of conjunctive queries. And the way we do this is we give in the paper, I mean, I gave a link to the paper on the title page. The way we do this is we actually just give semantic preservings and encodings in both directions. And it's kind of interesting maybe to think about what logically does it mean, what this formula means logically, right? So if I have some query C1 and C2 and I compose them, what does that actually mean logically? Well, it means that I existentially quantify along all the wires that I compose on, and then I take the conjunctions of the formulas in the middle. Okay, so I have to do some renaming, but that's the essential moral aspect. And maybe something I didn't say, but I probably should have emphasized, is obviously differently to the calculus of conjunctive queries that I showed you before, there's no variables here, right? There's no variables at all. There's no variables, there's no quantifiers, there's no substitution, none of the usual infrastructure. Okay, I told you that what we want to do is we want to axiomatize this notion, the semantic notion of query inclusion. So we want to sort of move from this very basic logic. Okay, so we have a logic which we draw as string diagrams, but we know we're just writing queries just as if we were writing first-order logic formulas. But now we want to find enough equations to characterize the semantic notion of query inclusion. Okay, so of course no one's going to be surprised that these equations include the laws of symmetric monodal categories. And I don't think I need to go through in detail for you guys what these are. So I'll just skip this. Now the interesting thing is that these copiers and discarders form commutative comonoids. Then the opposite version, of course, will form a commutative monoids. There's two additional laws that relate the monoids and comonoids, and that is the Frobenius law, which we all know and love, and the special law. Okay, and when you think about this, is kind of obvious, right? So, because you remember that the semantics of the commultiplication is just the diagonal relation. The semantics of this is the opposite of the diagonal relation. So when I compose these two, clearly I just have the identity relation. And I mean, this is all kind of obvious as well, right? So, and all of these things are just really very clear when you, well, it's easy to show it to be sound for all models. Because we have our notion of model fixes the meaning of all these basic components, right? So the structure always has to map to the appropriate structure in your model. Okay, but there's some more interesting stuff. So unit is right adjoint to co-unit. So that means I have two inequalities, right? So all of the previous stuff that I showed you, they were all equalities. We also need a few inequalities. So the bone is less than or equal to nothing. The identity is less than or equal to this disconnected thing. This is just, when you think about this, this is the full relation. So this is just saying that, in terms of any particular model, this just says that the identity relation is included in the full relation. And moreover, the multiplication is right adjoint to co-multiplication. And these are the triangle inequalities in that case. Oh, sorry, the unit and the co-units. Okay, so this is again kind of, I mean, none of these things are particularly difficult to see, at least see the soundness of. The final thing is that all relations are weak comonoid homomorphisms. Okay, so we don't quite have the thing that relations commute with the co-unit and the co-multiplication, but there's always this inclusion. And in particular, and when you think model, like again in terms of a model, when you're in rel times, this inequality is inequality precisely when R is total. This inequality is equality precisely when R is single valued. So in particular, when both of them are equalities, this characterizes functions. But obviously, not every relation is a function, but every relation satisfies these two inequalities. Okay, so what have I just shown you? I've shown you the nice way of writing down the definition of Cartesian bycategories, right? So the equations on the last three slides are those of Cartesian bycategories, which of course were introduced by Aurelio Carboni and Bob Walters. So another way one can say this is that every object has a commutative comonoid structure. This structure has right adjoints. I knew there was, I was trying to find, because I gave this talk once before, and I knew that there was an annoying typo, and I was too lazy to fix it. Okay, I'll put up these slides on my homepage after I fix all the typos. Every morphism is a weak comonoid homomorphism. Okay, that's the final thing that we saw. And somehow the claim in our paper is that Cartesian bycategories are a nice algebraic approach to relations, and I think that our results kind of emphasize the naturality. Okay, so as we saw, to prove the soundness of all of these equations is super easy, right? So the difficulty comes with, as always, comes when proving completeness. So just to remind you, we want to show that if we have sort of the valuation of one diagram being included as a relation in the valuation of another diagram psi, then we should be able to derive that phi is less than or equal to psi using this equational theory or inequational theory of Cartesian bycategories. Okay, so the first thing that one can note is one can restate all this using functorial semantics. Okay, so I kind of told you in a very roundabout way what is a model, right? So there's a much easier way of saying what is a model. So what is a model? It's simply a morphism of Cartesian bycategories from the free Cartesian bycategory on a relational signature to real times, right? So to the modular category of relations with modular product being the Cartesian product. So real times is kind of a canonical example of a Cartesian bycategory. It's like the set of Cartesian bycategories, if you like. And the free Cartesian bycategory on sigma, well, this is kind of, I mean, it's a syntactic thing, right? I just build up my string diagrams using the components and impose precisely the equations that I have to impose. Okay, so it has a very simple description. So why is there a one-to-one correspondence between such things and functors to rel? Well, when you think about it, right, once I tell you where a wire should go, that picks up a set, okay, and all the other stuff is forced on me by the structure of Cartesian bycategories, right? So, okay, so I should tell you what a homomorphism of Cartesian bycategories is. So it's a model of functor that preserves all the structure, right? So, so the fact that we're a model of functor means that once we say where the wire is, you know, once we say where the object 1 goes, then I know where any object will go because the objects of this are not just natural numbers, right? All the structure, like the multiplication, the co-multiplication, that has to map to the structure, the corresponding structure of rel, which in case of rel is the diagonal and the codiagonal, etc. So the only thing I really need to tell you is where the elements of sigma go, and sigma is the set of relational symbols. So I just have to tell you what the meaning of the relational symbols in my signature is. Okay, so it's just a really nice way of encapsulating this you know, bureaucracy of what it means to give a model. Well, now I can just say that a model is simply a functor from the free Cartesian bycategory on sigma to real times.
Probably a trivial question. Are you sure? How do you know that in rel there is like a unique common structure to which you can map stuff in CB? Like, couldn't it be like a lot of different pair of monoid, commanoid on?
Well, I'm talking about this is a Cartesian bycategory, right? So I'm talking about it as a Cartesian bycategory where that is precisely the Cartesian bycategory structure.
Okay.
Yeah, but in fact you can prove that it's unique. Okay, but let's just say, I mean, just to keep things simple, let's just say I have when I tell you what a Cartesian bycategory is, I have to tell you what that structure evaluates to, right? So let's just say that, you know, real times is understood as a Cartesian bycategory where, you know, multiplication, co-multiplication are always the diagonal relations. Okay, so what we want to do is we want to prove completeness.
Smallish question.
Yes.
Slide previously,
Yes.
the last line on the button, that looks like an instance of Unida. Like that.
This?
Yeah.
Wow. Okay. That's unbelievable insight because we're going to see more and more things that look like Unida as the talk goes on. So I want to know. I mean, maybe you can explain to me after the talk what you mean, what exactly you mean, because well, you'll see what I'll show. You'll see what looks like Unida.
Yeah.
But that's a very interesting thing to say. Okay, so the way we're going to do this is we're going to give a combinatorial characterization of the notion of free Cartesian bycategory on a signature. Okay, so I'm really going to characterize this thing not as terms taken modulo this inequational theory, but as something concrete, and in particular, we're going to look at these things as co-spans of hypergraphs. Okay, and it turned out that most of the work has already been done for us, right? So with a bunch of people, we had this paper, so Filippo, Fabio, Alex, and the other Fabio, we had this paper in which we wanted to understand how to do rewriting in monoidal categories from an implementational point of view, right? So if I give you, let's say, a symmetric monoidal theory with a whole bunch of equations, and I want to implement that in the computer so that the rewriting is done for you, then what's the data structure that I should use to represent my string diagrams, right? In a way that's going to make, for example, matching, like if I want to find the left-hand side of a rewrite rule in my string diagram, then I should be able to do this algorithmically. And when you actually look at the equations of monoidal categories, there might be a lot of sort of diagrammatic reasoning involved on paper, whereas you want that to be done for you by a combinatorial structure, or by some kind of data structure. So what we showed is we had this kind of a nice bridge that allowed us to go from purely equational things, so I'll explain in a sec what this means, and a category of discrete hypergraphs where the arrows are now not equational, they're really co-spans of hypergraph morphisms, where the objects are always just discrete, so they're always just sets of nodes, and then you have a hypergraph living in the middle. Okay, so I'll just explain what this is. This is just a free prop on sigma. Okay, and this is a chosen special Frobenius structure. And this is a coproduct in the category of props. So all this is saying is, I construct a free prop on some monoidal signature, and I have a chosen special Frobenius structure on the side, present. And this is an isomorphism of props, right? So really, this is as I said, this is kind of an equationally defined entity, and on this side we have a combinatorial entity, and we have an isomorphism. So this isomorphism is kind of useful because it gives us a bridge to go between these two worlds. And for example, if we want to do matching, then matching in here is just finding a hypergraph morphism from the hypergraph that represents the left-hand side into this bigger thing down here. Okay, so when you think about this, special Frobenius kind of already covers the equational aspects of Cartesian bycategories, right? Because in the special Frobenius, I have a co-multiplication, a multiplication. They interact together via the Frobenius law and the special law, which we have in Cartesian bycategories. So the thing that's missing from this, so to get from this to a free Cartesian bycategory, I just need to add the inequalities, right? So I need to add the adjointness of the multiplication, the co-multiplication, the monoid, and the unit and the co-unit. And surprise, surprise, we go back to this kind of original insight of Chandra and Milner. So it turns out that there's a natural order that you can put on cospans of hypergraphs, and we're going to let one cospan be less than another cospan precisely when I can find a cospan morphism the other way. Okay, so this should remind you of that first example slide that we had about the Chandler and Merlin construction. Okay, so one of the things one can now prove is that with this definition, this category of cospans becomes a Cartesian bicategory. There's a little bit of technicalities. So the usual definition of Cartesian bicategory is poset enriched. It's useful when talking about cospans to make it pre-order enriched so that we don't actually collapse non-isomorphic cospans. But this is really a very small technical detail, which is not that important. Okay, so the interesting thing is, okay, so we get the original Cartesian bicategory just by collapsing all of the equivalence classes with respect to the pre-order in the usual way. And moreover, we have this isomorphism between, well, we have this characterization of the free pre-ordered Cartesian bicategory on sigma as these cospans taken with this order. Okay, so why is this interesting? Well, this is where so I want to, okay, I'm kind of going a bit fast, but it's okay. So I want to first of all show you that, okay, we're interested in completeness for rel, but actually we have something more general. We have completeness for span set, and I want to show you how this works, at least give you a feel for how the proof goes. Okay, so first of all, I can order spans in a similar way to high-ordered cospans. So a span is less than another span if there exists a span homomorphism, in this case, in the same direction. Okay, so now I can consider, just as I was considering models of a free Cartesian bicategory, sorry, the model was the same thing as a homomorphism from the free Cartesian bicategory to rel. I can now consider somehow the models of cospans of hypergraphs in span of sets by considering homomorphisms of Cartesian bicategories. So there's something really kind of, so this sounds like a complicated thing, right? But actually, when you figure out what this involves, to the data, in order to give this homomorphism, in order to give this functor, this monodal functor, again, most of the data is kind of enforced by the fact that U has to preserve all the structure. So in fact, it turns out that to give such a thing is the same thing as giving a sigma hypergraph. Okay, so why is that? Well, when you think about what happens, so first of all, again, we have to kind of fix a set, right? Just in the same way that a homomorphism from the free Cartesian bicategory on sigma to rel, you have to fix a set. Again, here we fix a set. This is like the set of vertices of this hypergraph. And then for each relation symbol, so for each thing in sigma, I really only care where the actual sigma edge will go to, right? And to give the definition, to give the definition of U on that sigma edge will be to give a span in sets. Okay, and this is really just going to be the set of hyperedges of that type, of that sigma type. Okay, and here's now the kind of so having this in place, having this kind of piece of information in place that to give such a homomorphism is the same thing as to give a sigma hypergraph, we can actually characterize this functor. So once I know that, let's say U corresponds to some hypergraph G, then in general, this functor will now map a cospan to this span. And you see that this span has the Hom sets. This is completely determined.
And the individual components are just going to be Hom sets. So these are the ways you can map the set n into the vertices of G. And then the thing in the middle will be just a Hom set from G prime to G. Okay, and then once you have this characterization, which is kind of almost looks like a representability result, right, for this functor. Then the completeness proof kind of suggests itself, right? So this is some kind of it gives you some kind of a canonical model for any particular formula. Okay, so let me just spend maybe a couple of minutes on this, and then I'll start concluding. Okay, so we want to show completeness, right? So we want to show that for two cospans, if it happens that they are related by all models, so considering all morphisms from cospans to spans, if it happens that this is the case for all m, then we should already be able to derive this for cospans. Okay, so the interesting thing is, if this inequality holds for a morphism, it's going to hold for the model. So remember, models are the same, are in one-to-one correspondence with graphs. So I'm going to take the model that corresponds to this G. Okay, so what does it mean that it holds for this G? Well, it simply means that we have a morphism of hypergraphs of this form. Right? And then when you just take this commutative diagram, which is forced on us, as I said on the previous slide, and you just take, you just go where we know that there's at least one element here, right, which is the identity graph homomorphism. So if you just track where the identity goes to, this gives us a homomorphism from G prime to G. If you then see the fact that commutes is just the same thing that's, to say that commutes is the same thing as to say that then this commutes. And this is by definition that G is less than or equal to G prime as cospans, right? This is the order that we chose on cospans. Okay, so with that, we're almost there. I want to show you just a little bit of the technical details because it's kind of pretty. And to get the original theorem, remember, was for ordinary free Cartesian bicategories and ReL times. Well, if you think about it, the poset reduction of span set is ReL, right? So if I take two spans and I equate them precisely when there's homomorphism spans going in the two directions, I get ReL back. Okay? Obviously, poset reduction of the pre-ordered Cartesian bicategory on sigma is just the ordinary Cartesian bicategory on sigma. And then, because I know that this is the poset reduction, that ReL is the poset reduction of this is the poset reduction of this, and I have the completeness theorem upstairs, then it's not very difficult to show that the completeness of the inequational theory of Cartesian bicategories for ReL follows as a poset reduction. Okay, that's how we prove our main theorem. Okay, so somehow let's go back to the big picture. Right? So the big picture is about finding algebras for various kinds of relations. And in this talk, we really talked about maybe, let's say, the daddy of these, which is ReL times. I think in many different examples, ReL times seems to be like a touchstone. Maybe you have a forgetful functor to ReL times from your particular favorite category of relations. And we saw that somehow Cartesian bicategories, if you think of the language of Cartesian bicategories as a logic, then the expressivity of this logic is just the same as the expressivity of this classical calculus of conjunctive queries. And moreover, we have now a complete axiomatization of this notion of the semantic notion of query inclusion which is precisely given to you by the inequational theory of Cartesian bicategories. And as we saw, the way to get this result is you really sort of build on this combinatorial characterization of these categories of string diagrams. So somehow you have these three vertices of this triangle, and you have these really nice interactions between the three of these, right? So I think it's yeah, this is like this paper, this talk is a love, declaration of love to Cartesian bicategories as a mathematical structure. It's a very beautiful thing to think about, and somehow I think it's also very useful. Okay, and I think I'll stop. So thanks a lot.
Thanks, Pawel. And
So there is, suppose you know, there is this thing called AQL, that is basically database.
So what is it? AQL?
AQL
Uh-huh.
is basically a database system based on OLOGs that is being developed by David Spivak and other people.
Based on Prolog?
OLOGs.
OLOGs?
Yeah, they're
finally
basically.
presentable categories viewed as
Oh, okay.
yes.
Okay. No, sorry, I don't. Oh, this is okay. Yes. Okay. I know it vaguely. Yes.
So
Mhm.
their idea is basically doing categorical databases that I suppose they operate on like some flavor of relations of some kind. I would be curious to know if there are links between this thing and AQL, because obviously
I mean, like if you look at OPL, OPL is the operating, no, it's OPL, OQL. There's AQL, FQL, and OPL. And AQL is a very advanced one that you can do a lot of programming in, so that's really for migrations, but there is this operatic query language, which is very much the same idea, where the wires hanging out of the operator are the free variables.
yeah, my question was basically obviously they create a database, so they have a categorical way to do queries. And
Yeah, I have to admit, embarrassingly enough, that I don't know. I'm not an expert on that work, so maybe actually Brendan would be the best person to ask.
in the end,
Brendan, do you have anything interesting to say on this?
I mean, in the end, the logic they use is similar, because clearly they do conjunctive queries. So if they have another triangle on, like, or something similar, there should be links between what they do and what you do.
Well, let me say. I mean, I think the original. I mean, the thing that was done in this talk that hasn't been done before, I think, even in database literature, is that there haven't been axiomatizations of this notion of query inclusion, right? So you have this kind of the proof of decidability goes via this combinatorial reduction, right? But there wasn't I don't think there exists in literature an axiomation of this query.
Yeah, but
So I don't know if they have axiomatizations.
It's much more expressive, but doesn't have the same logical, the nice logical.
Yeah, you cannot decide answers.
But you
Yeah, but the
use
point is-
plan extensions to express. You can draw any diagrams you like and use that to query.
Yeah, but the point is, it is more expressive, still contains this logic as front.
Right.
So can I use this algebra somehow? Can I plug this algebra in AQL to basically do queries in an algebraic way instead of a relational way? My point is, can I plug and play this thing in AQL and use the other two sides of this triangle, at least with respect to that fragment of the language?
So effectively, yes, as long as you tailor the flexible accordingly, right? It's not going to take a day to get it all playing nicely.
Oh yeah, sure.
But yeah, you're right. This matches up really nicely.
Because especially the hypergraph thing means that somehow you can develop again, sort of like the bicategory thing
No,
means
it's
that,
not bycategories.
yeah, you have a graphical
Right.
language to express at least a subset of the possible queries that you can do into it.
Yeah, so I think this notion can be developed, and I've been planning to develop it further. I have fairly technical questions about that, so maybe I shouldn't ask them right now.
Okay.
Yes.
Well, you're welcome to.
Yeah, I think that's it.
So Alexander had to sit for this talk again.
Yeah, so that's true, and this is why I would like to ask you about the exciting new things you are not willing to tell us
Ah, yes. Well, this is, so basically, you mean this stuff?
Yeah.
The other exciting stuff to come soon. I know I should really ask Roman if he's comfortable with me talking about it. Okay, so Filippo and I had some very basic ideas along. I mean, that the next thing about LinRel, right? If you think about it as a kind of denotational model for open systems, is suitable for things that have a control theoretic flavor, right? So we use it for signal flow graphs. Also in this variant with Brendan that actually did the real signal flow graphs instead of the toy signal flow graphs we did with Fabio and Filippo. But in general, when you have relations over a field, so you have the kind of, both in the discrete and the continuous case, it seems to be a good fit for control theoretic things. Okay, so what's the difference between control theory and computer science? So how do you get models that start looking like computer science models, which are open, right? So what you do is you don't want linear relations. You want to take additive relations over the natural numbers, right? Because you have computations which carry real resources, of which you don't have negative resources. But you know that you can, if you have a computation, you have another computation, then you can sort of add them, which just means you do them concurrently, right? If you have enough resources, you can do enough things in parallel. Okay, so that gives you a natural notion of additive relation. It turns out you only want to talk about the finitely generated ones. And then, so we had some, so when you start looking at the equational theory, the white structure, you still have the white structure, but the white structure is no longer Frobenius, because the Frobenius of the white structure really tells us about the fact that you have additive inverses. So the white structure is actually a bimonoid now, because you have, for example, this equation, because this side tells you all the numbers such that when I add them together, I get 0. Well, if we're working over the natural numbers, then this is precisely when both of them are 0. Okay, so then you have two additional. So we were playing around with Filippo for a long time, for about a week in Lyon, trying to axiomatize this, and we kind of had some very basic ideas. And then Robin was visiting me a few months ago, and I kind of told him about this, and then he just worked it all out. So we have a complete axiomatization of additive relations. Then the other cool thing is that then Fabio got involved, and they also worked out affine relations. So you have an additional constant, which you think of it as a 1. Okay, now we can talk about affine relations. And also there's a really natural way of adding state to this, right? So just as we added state to signal flow graphs by this kind of register, there's a very similar thing you can do here. In fact, semantically, it's exactly the same. I mean, operationally, semantically, it's exactly the same. And then you have this really beautiful, expressive language in which you can do Petri nets, bounded Petri nets, all kinds of things, and with complete equation axiomatization due to Roman. So that's the exciting stuff.
If I can elaborate a bit more on this, I mean, shame on me, I didn't really got in contact with you, but I've been in contact a lot with Robin about this stuff. And yeah, basically you can use this stuff to do patronets. If you do gridded props, that is something Daniel is working on. I think he's really yeah, you can add states, and you can do, basically the idea is that in the end you get an equational theory for patronets. And the reason why this is very useful is that we have tools that employ especially logic programming and whatever, so that we take a patronet, you build a patronet in statebox, you have a corresponding term in that prop made of additive relations and some more stuff. At that point, this thing is just a set, it's just like a term. You can ask, can I reach this state from this state? This becomes a theorem that you want to prove in this equational theory, and then you just have a logic program that can do this for you. Incidentally, you can also basically run this thing natively at hardware level, and so it's fucking fast. So this is the prop that is a huge advantage by statebox with respect to other models, because it's like with this thing you're able to answer questions about your patronets very, very quickly. So
When you say statebox, what does that mean?
statebox is the project. Yeah.
From this degraded process,
Yeah.
you have.
Yeah. Yeah. This thing is like super.
We keep generalizing it now, generalizing some other stuff as well.
Generalizing, yeah.
Yeah.
Yeah, yeah. And by the way,